Hi, everybody. Now we're doing section 3.2, derivative of exponential and logarithmic functions. Because why wouldn't we want to do that? That's awesome. So the derivative of e to the x. So I'm going to go very quickly through where it comes from. I'm not going to go, this will not be a fully extensive proof. And for example, I'm going to start with the limit as h goes to 0 of e to the h minus 1 over h is equal to 1. I'm not going to prove that, but today. I'm not going to prove that in this class, but that's the fact. Now, once we know this, we're gonna take the derivative of y equals e to the x. So f of x plus h is e to the x plus h, which by exponent properties is going to be e to the x times e to the h. And then when I subtract off f of x, I have this guy right here, minus e to the x. I can factor out an e to the h, an e to the x, I'm sorry, and I have e to the h minus 1. When I put it over h, I get e to the x times e to the h minus 1 over h. I'm going through this kind of quickly because I just wanted you to get a sense of the proof. We're not, then for the derivative, I'm going to take the limit, but the limit we already were given. Again, I didn't prove it, but the limit of this whole sucker is equal to 1. So the derivative just winds up being e to the x itself. So the derivative of e to the x is e to the x, which is pretty amazing. And which is kind of awesome that it is itself. So the derivative of, for example, 5 e to the x minus 3x to the fourth plus 9x plus 16. Well, the 16 just disappears. The 9x, I just get 9. That's regular power rule. 3x to the fourth becomes 12x to the third. And the 5 e to the x is just 5 e to the x. I like that. And this one here, now this is interesting. It says x to the e. Well, x to the e is not, that's not the same thing as e to the x. And then you have e to the second power. Well, e to the second power is just a constant. It's equal to, I don't know, 9 or so. I don't know what it is exactly. Well, it's 2.7 times 2.7, so it's less than 9, but whatever. So the derivative of a constant is just 0, so that just disappears. The derivative of 2e to the x is 2e to the x. That's the exponential. That's the e to the x rule. But this here, that's not e to the x. It's x to the e. So that's really just a power function. So the derivative of this is going to be negative 7 times e x to the e minus 1, just like any power function. So it's a little tricky, but not hard at all. Yeah. Now, what about the derivative of ln x? Well, again, so first, ln logarithms, it's the inverse of exponentiation of exponents. And if this blue graph is the graph of y equals e to the x. This blue graph is the ln of y, the graph of y equals ln x, or as also b to the x. Sorry about that. Either way, you see that they're symmetric with respect to the diagonal, which means that they are inverse functions. And that's, as you know from algebra, that's a property of inverse functions. Now let's find the derivative of y equals ln x. So f of x plus h is ln of x plus h. F of x plus h minus f of x is ln x plus h minus ln x. But by log properties, that's the ln of this fraction, 1 plus h over x. Now, we're going to do something a little bit slick. We're going to say, we're going to divide both sides by h. We're going to pull the 1 over h out to the side. Then we're going to multiply by x over x, which is 1. Keep a 1 over x here and put an x over h over here. Then turn that x over h into an exponent, which is a log property. And now, this is how we want it set up. Because now when we take the limit, which is what we're going to do the next step, the limit of this sucker here is just e, because that was how we defined e, and ln e is just 1. So the final answer is just 1 over x, which means the derivative of ln x is 1 over x. That's pretty cool and awesome. The derivative of ln x is 1 over x, which is, again, very cool and very awesome and very amazing. So if I have y is equal to 3 e to the x plus 5 ln x, then y prime is equal to 3 e to the x, because that just stays the same, plus 5 times 1 over x, which is 5 over x. This is going to be 4x to the third minus. Now for this one here, I'm going to have to do a little tricky trick first. I'm going to have to take the exponent, the fourth power, and put it out as a coefficient, which again is a property of logarithms. And now I'm going to take the derivative. So it's going to be 4 over x, and that's going to be 4x to the third. So it's pretty cool, a little tricky, a little slick, and it works awesome. And what about logs and what about other logs and exponential, meaning other bases? So for other bases, the log of, so here's a nice little chart. The log of e to the x is just plain e to the x. The log of b to the x, or b is some other base, like base 2, base 10, base 17, whatever, is going to be b to the x times ln b. The derivative of ln x is 1 over x. The derivative of log base b of x is 1 over log b, times 1 over x. How come I don't see myself well? This whole time I didn't see myself. It's not that I'm obsessed with seeing myself, it's that I want you to see me. I want you to realize I'm a real human being. So this is what I was trying to say, by the way, that when you do calculus with base e, it's a little bit easier because the derivative of e to the x is a plain e to the x. I don't have to multiply it by some ln b or anything. And the derivative of ln x is 1 over x. I don't have to go dividing it by or multiplying it by 1 over ln b or something like that. So using base e actually makes the calculus a little simpler. Makes the calculus a little bit simpler. Let's find some derivatives. The derivative of 2 to the x minus 3 to the x. We'll do that one first. So that's just going to be 2 to the x times ln 2 minus 3 to the x times ln 3. Not so hard, just saying. It's a little bit more, it's a little bit, a little bit more complicated than e to the x, but not that much more. You just have to add in this extra log. And remember, this ln 2 is a constant. So I'm just adding in sort of really a coefficient. Now for number b, again, I'm going to be tricky and take that 5 exponent, the 5th power, and bring it out as a coefficient. So now my derivative is going to be 5 over ln 4 times 1 over x, which is following the rule that we just learned. And let's look at some examples. Price demand model. An internet store sells Australian wool blankets. I think there's a lot of sheep in Australia, if I'm not mistaken. Whatever they make wool from. I know they have kangaroos and koala bears. I know you're not. Well, I had a student last year. I had a student from Australia who told me, "Don't pet koala bears. Don't touch them. Bad things will happen to you if you do." That's what my Australian student said. Anyway, in internet social, if the store sells X blankets at a price of P dollars per blanket, then the price demand equation is P equals 350 times 0.999 to the X power. How do you know that? Someone figured that out already. Now again, it's a pretty good career, pretty lucrative career, pretty in demand career. Because companies love having these formulas worked out for them, so that it just makes things easier for them. Find the rate of change of price with respect to demand when the demand is 800 blankets, and interpret the results. Well, first we got to take the derivative of the p function. So that's the p function. The derivative is 350 times 0.999 to the x power times ln of 0.0999. And that's, again, the reason I have to stick in this extra part over here is because this was not base E, it was base 999. Now all I got to do is x is 100, just stick in 800 for x. Stick in 800 for x, and I finally get about negative 16 cents, which means when the demand is 800 blankets, the price is decreasing by 16 cents per blanket. Example 5, continuous compound interest. An investment of $1,000 earns interest at an annual rate of 4% compounded continuously. Find the instantaneous rate of change of the amount of the account after 2 years, and find the instantaneous rate of change of the amount in the account at the time. Ouch! That hurt. At the time, the amount is equal to 2,000. So let's just take a look. Okay, an investment of $1,000. Oh, so the amount A of t at time t is given by A of t equals 1,000 times e to the 0.04 t, which is that's our formula. A equals PERT. Remember PERT? That's the principal, the interest rate, and the time. And A of t is equal to 1,000. B to the t will be is equal to this thing right there. Why that's so important, I don't know, but that's what they're saying. The instantaneous rate of change is the derivative A prime of t, and we're going to just take the derivative. So the derivative is just going to be 1,000 b to the t times ln b, which is 1,000 e to the 0.004 t times 0.004, 0.04, I should say, which winds up to be 40 times e to the 0.04 t, which means after 2 years, A prime of 2, if I just plug in t equals 2, I get roughly $43.33 per year. And from the calculation of the derivative in part A, note that A prime of t is equal to 0.04, and 1,000 times e to the 0.04 t is equal to 0.048 of the t. In other words, the instantaneous rate of change of the amount is always equal to 4% of the amount. That's pretty amazing. So if the amount is 2,000, then the instantaneous rate of change is 0.04 times 2,000, which is $80 per year. This is a very, very slick strategy. I like this section, logs and Exponent. A lot of slick moves into here. Franchise locations. What are you going to start a franchise? Where do you locate franchises? How many franchises? What's going on here? Franchises. Okay. So a model for the growth of a sandwich shop franchise is N of t is equal to negative 765 plus 482 ln t. Where N of t is the number of locations in year t. Now t equals 0 is 1980. So I get maybe this thing started in 1980. I don't know. And by the way, how many of you guys were alive in 1980? I was. I don't know how many of you students were. And the rate of change of the number of locations is 2028. So we want to find all that and round both the nearest integer and interpret the results. Fine. So 2028, if 1980 is year 0, so 2028 is year 48. So we just have to find n of 48 and n prime of 48. Well, n of 48, I just stick 48 into this formula, and I get roughly 1,101. And for n prime, well, if I have to take the derivative, so the derivative of negative 7, that's a constant, it disappears. This just becomes 42 divided by t, because that's the derivative of line t. And I just plug in t equals 48, and I get roughly 10. 42 divided by 48 is roughly 10. So in the year 2028, there'll be approximately 1,101 locations, and this number will be growing at the rate of 10 locations per year. Someone told I know someone worked for Home Depot, and he told me that this is about like 10 years ago. He told me that there's a new Home Depot built every day. So that's kind of interesting at that time. So something like that. It was a 3 a day or 3 a week. It was a whole lot. Home Depots were built or every 3 days. Home Depots are just being popping out all over the place at that time. And that, my friend, is the end of this section. So it's been loads of fun, and we'll see you guys next time. Bye, everybody. Have fun.